Welcome to the NASCC, the Steel Conference. My name is Matt Kofchinsky. I'm actually the Pennsylvania Regional Director for McLaren Engineering Group. I'm also on the planning committee for this conference, so if you have any suggestions for future topics, you can see me afterwards. I'll be here for just a short time. We're going to ask that we silence all cell phones, please. We'll take all questions at the end. And would also like to ask that we don't take pictures during the presentation. It's a little distracting, and also, these slides will be available online through AISC afterwards, so you can get them then. This session is N28A, Solutions for Vibration Issues, Evaluations and Retrofits. PDH code is on there. It's 34717. Our speakers today are Dr. Tom Murray and Dr. Brad Davis. Dr. Tom Murray is a Emeritus Professor of Structural Steel Design at Virginia Tech. He is the first author of the AISC Design Guide 11. He has published many papers on the subject of floor vibrations, so he's an excellent presenter on this topic, and he's presented in numerous countries. He is a member of AISC and AISI specification committees, as well as AISC Committee on Manuals and Textbooks. He has received excellence in teaching from University of Oklahoma, Virginia Tech, the Commonwealth of Virginia, and AISC. In February 2002, he was elected to the National Academy of Engineering, and in 2012 was named a distinguished member of AISCE. He is a graduate of Iowa State University, Lehigh University, and University of Kansas, where he received his PhD. The second speaker today will be Dr. Brad Davis. He is an associate professor in civil engineering at the University of Kentucky. He has 8 years of experience in building design, emphasizing in healthcare facilities. He has approximately 24 journal and conference papers on structural vibration, has presented seminars and webinars on the subject to various industry and professional groups. I know both of these guys have been here before. Dr. Davis is a member of the AISC Committee on Manual and Textbooks as well, and he has served on a consultant for the Steel Solutions Center. He has received an Excellence in Teaching Awards from University of Kentucky, and he's a graduate of Virginia Tech, where he received his PhD. So without further ado, Dr. Murray, we're ready to roll.
Thank you, Matt, and thank you all for coming. As it says, we're going to talk about solutions for vibration issues, mainly cases where there are lively floors or lively other types of structures. To start with, this is one of these AIA continuing education parts of the conference, so we have to do a little front-end work here. The course description is building occupants occasionally report annoying floor vibrations due to human activity. Similarly, human-induced vibration levels occasionally exceed the tolerance limits of sensitive equipment that will be on the floor. In such cases, a retrofit solution may be or is necessary. There are 4 learning objectives here. This is all part of these AIAI requirements. I'll let you take a quick look at them rather than me reading them. And at the end, we get to ask you a question, so you can't go to sleep. All right, with that, the scope of the presentation is, first, how we would recommend you evaluate a floor, a problem floor, or a problem structure, but specifically a problem floor. We have found over the years that there are some questionable testing methods. We'd just like to point those out, talk about them very briefly. Dr. Davis will do that. And then some case studies. We'll take turns on a number of case studies where we worked on to correct vibration problems. The typical problem floor evaluation scenario is that the management may get complaints or will get complaints or did get complaints from occupants of the building. An engineer or sometimes a measurement company is then engaged. Hopefully, preliminary calculations are done to estimate the properties of the floor and the response to walking. Then a site visit to make measurements, very carefully done. Obviously, that data has to be reduced, report with recommendations made, and then possibly a retrofit. So let's look at some of these in detail. Preliminary calculations. We can go to AISC Design Guide 11, which is now the second edition. It was published a little less than 2 years ago. And or the SJI Technical Digest number 5 for a manual method. The manual method would allow us to estimate the natural frequency of the floor and also estimate the acceleration due to walking. The manual method only, though, applies to what are called regular bays, that is, rectangular bays, and works best if the surrounding areas are also rectangular or regular bays. If that's not the case, then there is a method in Design Guide 11, second edition, on how to use the finite element method to evaluate a floor. The process, of course, is to develop an FEA model, predict the natural mode, from which the natural frequency is there, of course, and then do a frequency response function, FRF function prediction. From that, the acceleration prediction can be obtained. Dr. Davis will go through that in a little bit. Once we get to the site, first thing that one needs to know is what is the natural frequency of the floor. And surprisingly, the most accurate and easy way of doing this is to do a heel drop. Simply roll up on the balls of your feet, hit the floor hard with your heels, but don't allow the balls of your feet to come up. That impact has a content of about 40 hertz, which nicely covers anything we would need and more than we need for a floor vibration evaluation. On the left on this slide is heel drop waveform from an actual heel drop on an actual building. That's processed using fast Fourier analysis to get a response spectrum, and from the response spectrum one can determine the dominant frequency, which in this case is, you can see it over on the left there, is 5 hertz, and maybe a secondary frequency that may be important later. So with that, then, we are ready to do some walking measurements. Now, the prediction methods in Design Guide 11 predict a peak frequency, a peak sinusoidal frequency. And the basis behind it is that walking is at a subharmonic of that frequency. So it is the maximum response that you can expect from the floor for any walker. Not from a particular walker, but for a walker who happens to walk at the subharmonic of the natural frequency of the floor. Your natural gait is that level. So we need to do timed walking to simulate what's behind what's in Design Guide 11. Problem floors are usually what we call low frequency floors. Means that the natural frequency is below about 9 hertz. And therefore, the occupant can cause resonance. I don't know how many times I've walked into a building with a lively or problem floor, and within 10 minutes, somebody will tell me that either Sally, who may weigh 120 pounds, causes the problem, or Joe, who may weigh 250 pounds, causes the problem. It's not necessarily associated with weight, it's their natural gait. And if their natural gait, walking through the office area, matches a subharmonic of the natural frequency, you're going to get the maximum response, and that's the one everybody is feeling or complaining about. Happens every time. So we need to cause resonance during the test. In order to do that, we need a step frequency. The normal range of step frequencies is 1.6 hertz to 2.2 hertz. So the walking frequency for the measurement has to be within that range if we're doing a reasonable test. Resonance occurs when a multiple of the step frequency equals the natural frequency of the floor. So for example, if we measured a floor that had a 6 hertz natural frequency, we're going to then start dividing that by integers. Of course, you know ahead of time what it's going to be, but in this case, we would divide by 3 and we'll get 2 hertz. We divide by 2, we get 3 hertz, that's outside of the range. Divide by 3, we get 2 hertz, that's within a normal walking range of 1.6 to 2.2 hertz. So that's the walking speed that's going to cause the maximum acceleration response. And that's what we're going to do to determine that response on the problem floor. How do we do this? Well, we use a metronome. It's used to monitor the walking speed. Structural engineers, I should say, have some trouble doing this. Most structural engineers don't dance, I found. So if the architect is there, we give it to him or her, and they do a much better job because, no, never mind. All right. Forgot this is being recorded. All right. We want to use multiple individual walkers because the impact from a particular walker's footstep is going to be completely different in almost all cases then, or somewhat different, I guess I should say, than another person. And we want to do multiple tests per walker. Now, you can use all kinds of fancy equipment to do this. The simplest set is what's shown here on this slide. This is a seismic accelerometer. It's very sensitive at low frequencies, and it's a bit expensive, and it's also something that normal vibration measurement companies don't have because they're looking at machinery in most cases, or something, or looking at a bridge, for instance, where there's traffic. We use a metronome, as I said, here in the center that any music store can sell you for 30 bucks in order to monitor the walking speed. And on the right is a handheld instrument that collects the data. This is an old, as a display is a pilot, Palm Pilot. Works just as well as anything else. And connected back behind here is a data stick handheld analyzer. The analyzer records the data and also can process the data, as we'll see. There are other systems, of course. Dr. Davis uses one with 2 channels or 4 channels to make measurements when he goes to a site. We get raw data. Raw data is pretty worthless, actually. In this particular case, you see on the left a 16-second record, which is what the data stick that I showed on the previous slide takes. On top of that, there is a low frequency signal. There's a low frequency signal, which is this one. It's only 6 seconds of this record with the 32 hertz signal riding on top of it. That's very, very common that you see either 30 or 60 hertz in these records because that's the equipment that's moving, that's operating in the building. And these accelerometers are so sensitive that they'll pick that up even though you'll never feel it. So the record has to be filtered. And it's filtered between 1 and 15 to 20 hertz. Below 1 hertz is of no interest. We as humans are not sensitive to vibration frequencies above 15 or so hertz. So it's filtered to that range. Also, individual peaks are not representative of what we feel. We don't go in there and look at the maximum acceleration at one point, okay? Because we're matching this to a sinusoidal or sinoid representation that's in the design guide. The tolerance limits in Design Guide 11 are peak sinusoidal accelerations, not peak particle accelerations. Many companies, measurement companies that are into other types of measurement work will report the maximum peak particle acceleration, which way overestimates, in some cases, what a human would feel. We use what we called an equivalent sinusoidal peak acceleration. And rather than repeat that over and over again in the presentation, we're going to call it ESPA. It's computed so that we can compare accurately what we're measuring with what's in the design guides. The way that's done is to compute first the maximum rolling 2-second mean square, or RMS acceleration, and then pick the maximum value of it in order to calculate the ESPA maximum value. So for example, on the record at t equal 1.8 seconds, the RMS is computed between 0.8 seconds and 2.8 seconds. And that's the RMS value then for 1.8. The maximum rolling RMS is then multiplied by the square root of 2 to get the ESPA. And the reason for that is if you have a pure sine wave, you multiply that by 0.707 to get the RMS value. So we're taking the RMS value and dividing it or multiplying it by 1 over 707 or square root of 2 to get it back to a peak value, which we'll then compare with the acceleration limits that are in the design guide. Let's take an example. Here's a 16-second measurement at a walking speed of 101 steps per minute. 101 steps per minute is 1.68 hertz. The natural frequency of this system, which results in, is equivalent to, I should say, a natural frequency of 5.06 hertz divided by 3. So on the left here is the filtered measured acceleration versus time, 16 seconds. The red line is RMS value multiplied by the square root of 2. The maximum value here is an acceleration. If you can't read it, it's 0.622% of gravity. The limit for quiet environments in the design guide, the recommended limit, is 0.5% of gravity. So the response here would be easily felt by an occupant in a quiet space. The walking was done at 1/3 of this frequency and was hit right on the button. There's the 5.06 hertz. And that's the amount of energy or maximum measured peak acceleration at that location. So if we have to retrofit, which we would for a case like this, or at least we would certainly recommend it because they already had complaints, possible retrofit options are to strengthen the supporting members. Now, to do that means we're going to weld something to the bottom chord or the bottom flange of the supporting members. And I emphasize welding. I tried many years ago every way possible to figure out a way to strengthen joists, for instance, using bolted construction, using turnbuckles, and it's just not possible. Humans are extremely sensitive vertical vibration sensors. 10,000ths of an inch right now where you're sitting, you would be uncomfortable. You would mention it or possibly even complain about it. Okay? So we're trying to reduce 10,000ths of an inch to 5,000ths of an inch. Whatever we put in there must be very, very stiff. So that's why welding is required. In addition, we have to get some strain into whatever we're adding to the structure. So we have to jack up the floor a little bit, 1/4 to 1/2 inch, then weld the reinforcement to the bottom chord or the bottom flange. Well, welding in an occupied building is not something that can be done most times. It's certainly not going to be cheap, and with computers in the building, that's extremely risky. So if the building is occupied, strengthening in this manner is usually not an option. Second possibility is to increase the mass of the floor. Usually that's not possible because of strength limitations. It takes a lot more mass, takes a lot of mass to make any effect on the response of the floor system. You can add more concrete. When you add more concrete, you get more mass, you get a larger moment of inertia, and you also get stiffness in transverse directions. If you're just adding mass in terms of concrete slabs or blocks, we only get one of the three parts that I just said to improve the response of the floor. Many times it's possible to install posts below a lively floor, especially if it's the same tenant. The posts have to go to grade. Where I realized this one time, I suggested posts between two floors. Couldn't go to grade because there was a parking garage below it. And the next day we took the post out because I had doubled the problem. If somebody on the upper floor did that, everybody knew it and knew why it happened. Now you get the response on the floor below, and they don't know what's going on, and they're not happy. So the post came out pretty quick. There was no way to go to grade. Done this by hiding the post or disguising the post as electrical drops or communication drops. They don't have to be a big post because we're dealing with only the loads from humans. And if they don't have a lot of capacity and the load changes, axial capacity, the load changes, they'll simply buckle and there won't be a problem. The other possibility is to add damping. And the only way I know of adding damping in the floor system is use what's called a tuned mass damper. And we'll talk more about a tuned mass damper toward the end of the session. Now, I'd like to go through an example project here where the floor was actually fixed by welding structural member to the bottom chord of the joist. This was an office building in Southwest United States. The shaded area there was partially occupied. It had work cubicles for full occupancy, but at the time it was only about 50% occupied. There were complaints there. They threatened to sue, so the engineer of record went to his insurance company. Insurance company hired a lawyer immediately, and then I was hired by the lawyer. The floor system is not unusual. It's 4-inch total depth, normal weight concrete, 1.5-inch deep deck. The joists were 24 VC, meaning composite joist, with a total load design of 300 pounds per foot. They were at 80 inches on center, and they spanned 40 feet. Along the outside here was a wall, so the support of the joist on that side was a wall. On the other side, grid line 2, it was a joist girder. The area where people were complaining the most is this smaller area shown here. And in fact, they had put 9 1-foot concrete cubes under various desks, thinking that that would help the vibration problem. I just happened to notice these. They didn't even tell me they were there. But it had, as we'll see here in a minute, very little effect. The predicted response of the floor without the concrete cubes was a joist frequency of 5.05 hertz, a joist girder frequency of 5.10 hertz, and then if you combine the two using what's called Dunkerley's equation, as it is done in Design Guide 11, it's 3.6 hertz. The predicted acceleration without the blocks was 0.99% of G, much greater than the quiet limit of 0.5%. Assuming a damping ratio, beta there is damping, a damping ratio of 2.5%. The way you get that is 1% for ceiling and ductwork, which was below, 1% for the structural system, and then 0.5% or 1% for the fit out, depending if it's what's called electronic office or a paper office. An engineering office being a paper office with paper and stuff all over the place. Electronic office one where there's just consoles and computer screens. Put the cubes in place, you can see how little change it made, right? Reduced the frequency by a little bit. This is all predictions now. The frequencies by a little bit and change this by 0.01%. So it was really a waste of time and money to do that. All right, we went out and measured. The cubes were there. Like I said, they didn't tell me were there, and I just happened to notice them. The measured frequency was 4.1 hertz, somewhere between the bay frequency and the joist frequency. And we did walking, as I said, this time at 205 hertz, which is 1/2 of the 4.1 hertz, or 123 steps per minute, which is in the range of normal walking. At a 200-pound man, 210-pound man, 160-pound man. And look who caused the largest acceleration. The 160-pound man. He was much better at walking he was a lawyer. At walking at the metronome than the engineers were. There was also a woman who could really get the floor moving, and they didn't want me to ask her to walk that particular day. So the accelerations, the measured accelerations, the predicted accelerations are greater than 0.5% G, and it was decided to retrofit this building. What we did is we removed the concrete cubes. We then, through finite element analysis that Dr. Davis did, decided that we could, if we stiffened the joist by welding W10 by 15, 20 feet long to the bottom chords, we could reduce the predicted acceleration to a little over 0.6% G. And then, if that was not satisfactory, could go back in and stiffen the joist seats on the joist girder to increase the composite action between the concrete slab and the joist girder and get it down to a little over 0.5% of G. Well, in order to do this, they had to remove the tenants from right below it. They put them in a temporary place. It took a lot of negotiation to get the people to agree to do that. It was full of computers, but they were willing to make the fix. And you can see here where remember I said 15, that can't be a 15, what a W, whatever they were, are welded to the bottom chords of the joist, where they're welded only at the panel points. Required removing the ceiling, of course, and a set of 3 or 4 joists were jacked up, and the beams welded on it, and then they just moved across this whole area, not just a little area where the concrete blocks were. With one bay completed, I was asked to go back. The measured frequency was now 5 hertz. So the walking is at 1.67, 5 divided by 3. The 209-pound man, I guess he lost a pound in between times. Response was 0.46% of G. The 170-pound man got it down to 0.31% G. And this time, we just waited long enough until this lady walked through and everybody was okay with her. So accelerations were down to 0.5% G. The owner, the occupants agreed that, the tenants, I should say, not the owner of the building, agreed that the retrofit was successful. The ceiling was put back up, the people moved back in, and that's the end of my story. So with that, I'd like to turn it over to Dr. Brad Davis to talk about a number of things.
Good afternoon. I'll start with a short section on our questionable testing methods that we've noticed over the years. And the first, as Dr. Murray mentioned earlier, is the use of these peak particle velocities or accelerations in the measured records. As you can see at the bottom left here, we have a measured vibration waveform, and you can see that the equivalent sinusoidal peak acceleration is, this thing was working a minute ago, now it's not now, is 0.531% G, and the peak is about here, that's 0.875% G. And this is fairly common. This is with a filtered record. If it was unfiltered, that could have been way higher than that. Now, that peak is just not representative. The perception of the people on the floor is not going to be super affected by that. They're going to be affected more by the more persistent vibration, and that's represented by the ESPA. So we really want to be looking at the ESPA. And as you see on the right there we have the tolerance limits from Design Guide 11, Chapter 2. And those are sinusoidal peak accelerations. That's what those are. Those are not just the peak or zero to peak, or there's various other names for it, or the PPA. It's not that. It's the sinusoidal peak. So that's why we want to use something other than these PPA or PPV records. Okay, next, long-term monitoring. I think this has some potential, but there are some things we have to be aware of, and some things that we need to caution you about. First is these really need to be paired with video monitoring so that you know what caused the vibration events. You can see on the right a 2 minutes of a 2 minute chunk of a long-term monitoring record, and we can look at those and kind of guess at what caused them, but we're not really sure these individual events. So we really need video monitoring there. Even that's going to be a little tricky though, because we see that leg jiggling and there are other excitations that the video monitoring may not capture as well. So it's a little tricky there. This is why we like the type of test Dr. Murray described earlier. Okay, I've also seen a few comments about using cell phones for measurements. Of course, all of our cell phones have accelerometers in there. First thing about this is our vibration measurements require extremely detailed control over many parameters, ranging from the sampling frequency, the range of the input, voltage, bandwidth of the measurement, and so on. There's lots of different parameters that we control with, we spend a lot of effort trying to control those just exactly so. If we have very simplified equipment, we're not going to have that, so we need to watch out for that. Then the last part there is the floor vibration levels that we're measuring are very, very, very low. Very, very low, because humans are so sensitive. This is not like putting your iPhone on the side of a piece of machinery that's vibrating a lot. It's a totally different animal. We need to have very, very sensitive accelerometers at very low frequencies. So just some cautions there. There's definitely some potential there for some success as well, though. With some more equipment being developed and analyzers. Okay, now let's jump into 7 case studies that's going to round out our presentation. And I'll just read these really quickly. We have an office floor that's converted to a lab floor, so the tolerance limits are more stringent. We have a very light and lively floor. We have an office floor, just a plain office floor with complaints. We have one multi-story building that has aerobics activities on various floors that cause a fairly interesting problem. We have a hotel crossover, like a pedestrian bridge-like thing that had some interesting issues as well. We have my personal favorite case study of all time is our monumental stair that Dr. Murray will tell you about near the end. And finally, we have a short case study for short discussion of tuned mass dampers. Okay, so let's start with our first one. This is an office floor that was converted to a lab floor. This floor construction was a 3-inch normal weight slab, concrete slab with 9/16" deck, open web steel joists. You see a 24-inch joist at 3 feet spacing, and they're 33'6" long. And the girders are W24 by 68, and they are 30 feet long. So this is fairly typical. And this floor had done just fine for years supporting an office occupancy. There were no vibration issues with this floor for that occupancy. Well, they wanted to change the occupancy to a lab, a pretty small lab. And in this lab, they're going to have bench microscopes with up to 100 power magnification. If you go in Design Guide 11, Chapter 6, you see that the tolerance limit for those is 4,000 microinches per second, and that's a 1/3 octave velocity limit. Okay, and just quick note here, there's a parking garage below, so that's going to limit any kind of retrofit activities that we can try. Okay, so let's see what happened here. So our strategy coming into this, we suspect that they're going to have trouble. We just assume that coming in just from some quick preliminary calculations. So here's the strategy. We're going to go there, measure the vibrations due to walking in a bare slab condition, which is obviously very conservative because there's very little mass and damping there. If we happen to get all of our velocities below 4,000, we're good. The floor is fine. We know it'll be way lower than that in service, so we would be finished in that case. All right? Okay, if that's not true, go to step 2. If the velocity exceeds the tolerance limit, then we will then use the data from the first step to help us predict the in-service response. If that's less than 4,000 microinches per second, then we're finished. We move on to some other project. Fine. Okay. If that's not true, move to the last step. If the predicted velocity exceeds 4,000 microinches per second in service for the prediction, then we use the measurements from the top bullet point to help us design the retrofit solution. So this is our strategy moving in. You see, we have a slightly different strategy on many of these projects. It's just we have to sort of think through what to do depending on what's going on and what's required. Okay, so let's talk about our measurements. You can see at the top right a little plan that shows that we put in. I'll just zoom in on this one bay for discussion. I looked at several bays. So we have an accelerometer in the middle of the bay. That's at the worst location. And we have a couple of walking paths. Path 1 is going perpendicular to the joists, and path 2 is going parallel to the joists. Okay, so the heel drop results are down at the bottom there. And you can see the waveform on the left. We have about 5% G. We can't get a precise evaluation from that, but that's a pretty high value, not huge. But then the thing we are really looking at is the spectrum there. And you see from the spectrum that we have a 6 hertz natural frequency. It's 6.02 hertz right there. All right, so moving from there to the walking tests, this is a small lab, not a lot of people in there, not a lot of room to walk around. So we use very slow walking, which is a category in Design Guide 11, Chapter 6. That's at around 75 steps per minute, which is pretty slow. You can walk that slowly, but that's getting near the limit. Okay, so our measured, also we had 2 walkers walked about, I forgot how many times each, decent number of walking tests. Okay, so the velocities range from about 12,000 microinches per second to about 25,000 microinches per second, and the average was 17,500. Of course, that's far higher than the 4,000 microinch per second limit, so we're not done. We have to continue the project on, go to the next step. Okay, now next step is to predict the response in service. So we want to come up with a prediction method. Now, one of the cool things about having the data from step 1 is that we can calibrate our prediction method. We can make it more accurate. We can sort of tune our method to make it more accurate. Okay, so we start with the natural frequency prediction from Chapter 6 of Design Guide 11. And in there, we calculate the frequency a little bit differently than in Chapters 4 and 5. Here, we take the minimum of the joist and girder natural frequencies. We take that. Now, the calculated values here, we had for the joist frequency, we had 6.49 hertz, and for the girder frequency, 6.18 hertz. So the min of those two is the natural frequency of the bay, or 6.18 hertz. That's our prediction anyway. So we take our measured divided by predicted, and we get 0.974, so it's quite accurate. It did a very good job at predicting the natural frequency. That's the easy part, is getting the frequency. Okay, so we're good with that method. We don't need to mess with it. We're fine there. Let's go on to walking. Just looking at the waveforms from the tests, I sort of just judge that they're somewhere between a resonant buildup and just pure impulse response. So I took the equation 6-3a from the design guide, which has a resonant response part here, an impulse response part there, and I calibrated it especially for this floor. So I could come up with a calibration factor change. I'm changing these factors here and here just to make it match up very well for this floor. So I'm increasing the accuracy of our predictions with the luxury of this design, or with this measurement data that we had. Okay, so in service then, this method, in service we have more mass, obviously. So we add that to the calculations. I stuck with the 4% damping ratio because I just couldn't stomach going any higher than that. We just couldn't do it. I want to be conservative. We had 4% measured, which was pretty high for that floor in that condition. Okay, so using our method, we came up with almost 25,000 microinches per second predicted. So that's obviously way higher than the 4,000 microinches per second. So it's no good. So now we can move to the third step. We have the retrofit required. Okay, so let's use the calibrated method now to design the retrofit. Tried various options, and this is what I settled on. We have 4 W16 by 26s in each bay. Just put them between the joists. Put them nearest the middle of the bay as you can to get where they're more effective. Also extended the bottom chords of the joists to increase the effective mass or effective weight of the floor. And then finally, the girders are kind of a weak link here, so I wanted to weld little pieces of HSS between the top flange of the girder and the underside of the deck. Welded in there to make the girder act compositely for vibration. That's going to really help a lot. Now, our predictions now for this system, I have 7.3 hertz. So it's up a little over. It was like 1.4 hertz up now, so that's very helpful. We have a much higher effective weight because we get continuity with the adjacent bay up the page there. We have continuity with that. And with those, we have a predicted 1/3 octave velocity of 3990 microinches per second, which is less than 4,000, the limit. So we're good. So we recommended that use that option for this floor. Okay, there's one. So we converted this office floor to a lab floor. Okay, next we have a pretty awesome case study. This is what we call the light and lively floor. It's very light and lively. So this is a large condominium building, and it had a very light floor system. Probably the lightest one I've ever heard of. It had a 13 PSF slab weight, which is like almost nothing, right? And it had very light trusses supporting the floor. Light steel trusses supporting the floor. Trusses were about 14 inches deep, if I recall correctly. Okay, so we had 2 areas that had trouble. On the right, you see the common area that has a pool table, fireplace, cooking and dining area. Pretty cool looking area. And on the left, you have a gymnasium, just like a workout area. Now, the rest of the structure had typical apartment type rooms, like the hotel room you stayed in last night. Probably they were laid out like the whole rest of the area. The whole rest of the building was laid out like that. There were no vibration problems there, even with this system. In these areas, though, these stack. So they have these large open areas, and there it was extremely lively. Just an extremely lively floor. Okay, so site visit. Went there, see what's going on, and measure the vibration. So this is in the common area. We'll talk about it first, and then the gym area. You see, we have 4 accelerometer locations shown on the right, and we did heel drop tests at all 4 locations, and we did walking tests at 5 different walking paths shown there, with 2 walkers walking several times each to get a pretty large amount of data. Okay, so what do we get? Heel drops at location number 2, just going to one of the accelerometers to talk about it today. We do at all of them, obviously. You can see the heel drop peak acceleration of 19.5% G. Now, we can't evaluate the floor with that because if you hit it harder, you'll just get a bigger number, but that's just out of this world. That might be the highest one I've ever seen. That's pretty huge. You can really feel that. Now, the natural frequency was 7.12 hertz. As you see in the heel drop spectrum at the bottom middle there, that's at location number 2. And we have 7.12 hertz as the natural frequency. One interesting thing was we have a wall there between the common area and the conference room to the planned north. That's where the one on the right is. There was almost no vibration over there because of excitation in the common area. So there's almost no transmissibility over there, which is kind of interesting. Okay, so we have 7.12 hertz, which is not super low, but if I have this low of math, I need a really high frequency for it to work, and that's not very high. Now, walking tests, we're going to walk at the 4th subharmonic of the natural frequency, because you can't walk fast enough to hit it with the third subharmonic. So that's 107 steps per minute, and our ESPAs range from 1.03% G to over 3% G. The limit for this area is about 0.5% G, so it's just out of this world crushing it, right? It's just way, way off. Okay, now, we also know that the max was walking along path 4. Subjective evaluation, awful. I mean, it's just terrible. I mean, strongly perceptible. I mean, you can really feel this vibration on this floor. It's very, very perceptible. There's audible rattling. You can hear things rattling when you're shaking the floor. You can stand like this and just bounce a little, and you can hear things rattling on the floor. Like stuff on, pictures on the wall. There was a vase sitting here that was jiggling around on the table, and you could hear it across the room. Finally, there was even visible motion. There were potted plants, and you could see the plants jiggling around as you're walking or moving on the floor. So this is a very, very lively floor. Okay, so here's just a picture of the maximum ESPAs. It's the waveforms, and you can see we have a pretty good resonant buildup there, and the one on the right is 3.3% G. 0.5% G is what you see where it'd be on that picture, way down low. So we're way higher vibration levels than what they're going to tolerate there. So we needed some kind of a vibration reduction strategy. Okay, so we want to use we need to come up with a method to predict the natural frequencies and walking accelerations, so then we can use that method to then investigate retrofit options. This is our pattern. We chose to use finite element analysis in this case. We use it pretty frequently because it has more flexibility. It provides more flexibility for investigating various options. We use chapters 4 and 5 manual methods when we can, and 6 manual methods when we can. Finite element analysis comes in pretty handy for stuff like this. Okay, so first step, we want to predict the FRF magnitude for location 2 for our discussion here today, because we want to compare that with the heel drop spectrum. They should be about the same shape. And also, we need the FRF magnitude to predict the walking-induced acceleration. Okay, so natural frequency. From this, let's see what we have. At the top right, you see the heel drop spectrum. At the bottom right, you see the FRFs. The black is the FRF for the untuned model. You can see it is about the right shape. We're not going to nail this. This is a pretty good match, actually. But the FRF is shifted to the right about 0.65 hertz. So it's just a little stiffer than reality. So just by trial and error, I want to move that to the left where the red one is there, just by making the joists more flexible. In this case, I have a 15% reduction in the moment of inertia. But if I had to change things a whole lot, then we start thinking our model is just not doing a job, right? Here's just a small adjustment. Okay, so our method for then predicting the walking-induced acceleration, we have what we call the FRF method. This is version 2 that we're trying to develop now. It's going to be a replacement for the FRF method at the first part of Chapter 7 in the Design Guide 11 whenever we get it totally nailed down. It's going to look like this. Now, in this case, I have an R factor there, and I'm going to calibrate this method to match up as best I can with some of the walking measurements. Once I have it calibrated so it's matching them, then we'll use it to predict what will happen with the retrofit option. So you see at the bottom there, for Walker 1, I'm mainly concerned about him. He had the most response, or the highest response. So I calibrated it to match up with him. So I have 0.997 measured over predicted, because I've shifted it so that the predicted matched up with the measured. The Walker number 2 is off a bit there. It's a bit conservative for that Walker. Just can't get it totally matching up. But this is good enough to move on with our retrofit evaluation and design. Okay, so what's our problem here? We need to figure out what are we going to try to do to the structure to bring the vibration down. Well, the main problem was it just has no mass. Even with the superimposed mass, we have something like 25 psf, which is almost nothing, right? It's way low. It's like 3 times lower than what we would expect. Okay, so we have some limitations. We have limited ceiling space. The drywall is screwed right to the bottom of those trusses, so we don't have any ceiling that we can do anything interesting in. We can't really put any columns in there. Below the gym area below, there's even a bigger atrium type area, or like a, I don't know what you call it, just a big open area. There's no way to get a column down there in most of those areas. It's an occupied building, so we can't add large beams. That would have been about like taking an 18 by 35, 30 feet long down the corridor of the hotel room hotel you were in last night. So we can't really do that. So our approach here is to just add a large cold form channel to the underside of the bottom cord, and add a couple of heavy shorter channels to the top cord and just screw them in there to get more mass and stiffness. Okay, so here's a picture we have on the left, the unretrofit. You can see the trusses there, and on the right you see we have these 12-inch channels there, the heaviest ones we could get, and have them screwed in there, and you probably can't see the top cord channels as well though. So we have all those in there just to get a lot more mass and stiffness. Our backup, by the way, if this didn't do it, was to take rebar and put padding on them and put that sort of perpendicular to sort of just keep adding rebar in pieces until we had enough mass that way. But we're trying anything. So this is going to work. Okay, so we start with a tuned model and method. We modified the joists in the model, and so we end up getting a natural frequency, or we have the FRF that you see on the right in red. So the black is the tuned unretrofit, and then on the right you have the retrofitted. Push the natural frequency way up, and the predicted peak acceleration, sinusoidal acceleration, peak acceleration is 0.539% G, which is near the limit. The owner accepted the performance of this. Couldn't get back in there to retest this because they didn't want to maybe open up another can of worms. They said, let's leave well enough alone, move on with our lives. Okay, so that's the end of that one. Pretty cool. Now, the gym area. We have a pretty neat approach here. We'll talk about it briefly. Down there, we have a site visit with 4 accelerometers as well. You see the locations there. And we have heel drop tests, walking tests with 2 walkers, walking in various ways. So here on the left, you see the heel drop test spectrum. You have 8 Hz natural frequency. On the right, you see one of the waveforms for the walking test. This is the one with the highest response at 1.75% G. So it's also way over the limit. Strongly perceptible vibrations. So we need a retrofit there as well. And this one's neat mainly because of how out of the box our solution was for this. We have this wall that they thought actually might look kind of cool in the area. And we hid a steel truss in that. We hid a steel truss in there, and you see it in the model. This is the reason why we use SAP for this, for the finite element analysis, so we can analyze something like that and see what happens. And this was predicted to reduce the vibration levels by about 50%. And according to the owner and contractor, it felt very solid. They were happy after this. So that was a pretty cool solution, we thought. Okay, now let's move on to a different kind of problem. In this case, we have a regular office, and it has this is a call center, so there's people sitting in these office spaces that you see in the architectural plan to the left, and they just sit there in their cubicle offices pretty much all day. And this has typical composite framing. On the right, you see we have a 40-foot long beam, W18 by 35, at a 10-foot spacing. We have a W24 by 68 interior girder that is 30 feet long, and it has a 5.5-inch normal weight concrete slab with 2-inch deck. So it's a pretty good looking system. You're not really expecting any trouble out of this system. However, the tenants started complaining almost immediately after moving in, so they think it has some serious vibration. Okay, so let's talk about our site visit. We went there, and I'll just zoom in on this one bay. This is a huge building with many bays. This is just one of them. We will talk about it only today. Okay, so we go to this bay, put an accelerometer at the middle of the bay, and do a heel drop nearby, like just off to the right there. Just do a heel drop there, and you get this waveform at the bottom left and spectrum at the bottom right. You can see in the spectrum we have two natural frequencies that are close together. We have 4.8 hertz and we have 5.45 hertz, and both of them are fairly lively. That's pretty interesting because of what it does to the waveform. If you look at the left there, you'll see this beating phenomenon. The vibration damps, kind of decays down, comes back up, down, up, and the frequency of that beat is at the difference between those two frequencies in the spectrum over there. And you'll get this if you just go into Excel and plot a couple of sinusoids added together at two different frequencies, you'll get that. It's just as simple as that. So people find this particularly annoying. Okay, so we have that. Now, for the walking tests, we don't know which one of those two frequencies is going to cause the highest acceleration, so we do both. We start with 4.8 hertz natural frequency, divide that by 3 to get the step frequency 1.6 hertz, and do the same thing with the 5.43 natural frequency. So we have 1.82 hertz for that. So we walk both of those. Just do all the tests twice. Okay, so we have 4 walkers ranging from 185 pounds to 230 pounds, and we walked a whole bunch of times each, along paths 1 and 2, which are obviously controlled by the furniture. Okay, so just summarizing the walking tests, the maximum was only 0.415% G, and that's the one you see on the right over here. That's a pretty decent resonant buildup, but we just don't have a whole lot of response there. Okay, the average is only 0.226% G, which is really nice. That's pretty cool, and no problem there. We're even trying to get it moving, and we're getting 0.226% G. Okay, these are far below the 0.5% G limit that we would use to design this floor. My subjective evaluation is I could barely feel the vibration. I felt it slightly distinctly once early on. I don't even know if I felt it after that. I mean, I felt it just a hair a few times, but there's not a lot of vibration there. They act like the floor is scaring them so bad that it's going to fall on their head or something. But I really couldn't feel it. So there's some psychological element going on here as well, but I don't know what that is. Okay, so now what does Chapter 4 say about this? Because Chapter 4 is our gold standard. We've studied it to death, and it's been used for well over 20 years now, and it's extremely accurate at predicting whether there should be complaints or not. We only have 0.025 for the damping ratio because all we have is a structural system, which gives us 0.01, the ceiling, which is another 0.01, and then 0.005 for the electronic office. We have 12 PSF from the ceiling and the electronic office. And you go through here and you see these frequencies and the peak acceleration of 0.474% G. So it looks good. Now I would have used this system, no question about it. But there's still complaints. So what are we going to do? This is a huge tenant, big building, and I can see them moving out. So we really want to make them happy. So then for our client's sake. So we need to reduce the vibration even farther, or even lower than that. So let's zoom in on this bay and see what we did here. This is that electrical drop solution that Dr. Murray mentioned. We had columns at the corners of these spaces, or corners of these desks, that look like electrical conduits. Like, for example, an HSS 3x3 column. And the idea there is to increase the natural frequencies. Okay, so we're going to have to resort to our finite element analysis for this because it's a weird arrangement outside the scope of chapters 4, 5, and 6. So we have to do this here. So we're going to use our version 2 of our FRF method again, and I've tweaked it and calibrated it to match the test results on this building to use on this building. The calibration for all buildings is not complete. Have not gotten that done yet, but I can do it for this building. So we're going to use this now. Here's what we get. We have our predicted natural modes on the left there, and you see the predicted FRF and then the measured heel drop acceleration spectrum on the right. And the FRFs really did not require very much tweaking at all to line them up. So this is better than normal. You can't always do that. You just cannot. Getting frequencies is pretty easy. Lining the FRF up, which is more important, is way more difficult. And sometimes you just can't seem to do it. Here, lined up pretty well. Now, I adjusted the R factor on this modified FRF method to make this peak acceleration line up with the measured. So we have 0.415% G. So see, I tuned the prediction method because I have the luxury of having the test data, and it just makes our predictions much more reliable. Okay, so now take that tuned model, now add columns. And you see what we have here. We have our predicted natural frequencies and or natural modes there, and the FRF on the right. And you see that the natural frequencies got pushed way over to the right. There's way stiffer now. And the peak acceleration that is predicted is 0.184% G. That's less than half of what it was before in the previous slide. So it's less than half the 0.415. So it's already good. It's twice as good now. So surely they'll be happy now, right? So that's what we recommended, and they might be building that about now. So anyway, with that, I want to turn this back over to Dr. Murray because he has these last few case studies.
These are just a series of short examples of what happened to folks very unexpectedly. This is a 10-story building, obviously. These areas in here in New York City are actually leased to Broadway and off-Broadway play folks where they do the practicing. And right after this building was completed, they were practicing for the 42nd Street musical on the 4th floor and got complaints from the office people on the 10th floor, which kind of shook everybody up. We went there and we measured, well, first off, we got a small dance group so they could do it very well, not structural engineers. And the natural frequency of the 10th floor was 4 hertz. So we did 2 hertz dancing on 4th, 6th, 7th, and 9th floors. These are the waveform records, 16 seconds long, measured on the 10th floor. Down here on the 4th floor, those 2 red lines are 0.5% G. Remember, this is not on the 4th, this is on the 10th. On the 6th floor, you can see they're above 0.5% G as well as here. We did it on the 7th floor, that's 1%, and on the 9th floor, that's 1%. We found that 50% of the motion on the 10th floor was actually caused by axial deformation of the columns. From 6 people dancing on the 6th floor at 1/2 the natural frequency. Now, some years ago, I showed this, and the guy stood up during the question period and said, "I don't believe you." In case that happens today, here's a paper in engineering structures of the same kind of thing happening in a building in Seoul, Korea. It's a 39-story building, picture it over here. They were doing this thing, I don't quite understand what it is, but it's a rhythmic exercise on the 12th floor. The global natural frequency of the building was 2.7 hertz, and the exercise was exactly 2.7 hertz. People on the 34th through the 39th floor thought there was an earthquake, started complaining. They couldn't figure out what it could possibly be until somebody realized this was going on 12 stories below. And again, the only way this can happen is the energy to go up the columns. And if you do something at resonance and there's low damping, it takes very little energy to make it work. So that's proof that what I did is right. All right. Here's something else that happened to a poor structural engineer. This is a hotel crossover. And the beams were W16 by 31 by 30 feet. The slab was typical floor slab. He just looked at it and said, it's not going to be a problem. Unfortunately, that's where the slab was. All right. So the predicted, or the measured frequency for this condition is 9.35 hertz. Predicted acceleration is about 1% of gravity, which is less than 1.5% recommended in indoor footbridges. And what he got was 4.71 frequency, hertz, and an acceleration of 4.4% of G. One time I showed this in a talk, and the guy in the back of the room said, "Oh," and you can fill in the blank. And I laughed because I knew what he was talking about. He had actually done exactly the same thing. What was the fix? Well, this one was really unique. They didn't know this was going to happen. Scaffolding was underneath it because they were painting the soffit and so forth. And it was one of these a crossover at every floor. So they took the scaffolding down about 10 days before the hotel was to open and found the problem. What do? Well, after making some measurements, I suggest that they pave it with lead. Why lead? Because otherwise you would have had problems with the handrails if you went in there with concrete. There was no way to get back underneath. And if you went in there and put in any concrete blocks or whatever, then the handrail would be out of code. Lead was heavy. 1 inch. Hope the guy who was measuring the handrail made a mistake. But they couldn't get the lead quick enough. So the architect came in with carpet and undermat and padding and just kept piling it on the bridge until it was about 4 or 5 inches thick. Said, this is it. And you had to wade across this bridge to keep it from vibrating. It was an absorber. They opened up the hotel with that fix. This is a monumental stair that Dr. Davis mentioned. This is a plan of the stair. There were 4 cables at each one of these landings, wire ropes, to support the landing. Beautiful stair. Okay, you can see it here, and there's the wire rope. What happened? The building structure was nearly complete when the stair designer, fabricator, finally provided a design for the stair with the wire rope. The engineer of record for the building just added some secondary members up underneath the slab above. Didn't think anything about vibration. Didn't think any way somebody walking up and down stairs can cause a problem. The stair was erected, building opened, and instantly there were major complaints from the people in the offices on that floor above. Went there and made measurements. This is in the office. One person walking down the stairs, descents are always worse than ascents. 1.8% G. 4 people walking down caused 3.25% G. And this stair led from offices down to an auditorium, so you know people are going to be running down going into there. You literally could not keep a pencil on a piece of paper when 4 people were going down the stairs. So obviously a retrofit was required. You can strengthen the stair maybe by adding additional stringers. They were going to have to be pretty deep, and the architect didn't like that. Possibility of installing columns between B1 level, which is the basement down below, and the level in the 2 landings above, or the consideration of using a tuned mass damper. This decision surprised me. They actually put in these things right here and right down there, left the cables in place, left the wire rope in place, remeasured it on the office floor above, and the acceleration for 4 people running down the steps give us down to 0.239 or 0.24% G, and everybody was happy. Briefly, the use of tune mass dampers. What's a tune mass damper? Well, you use it every day in your car. Your front suspension system is a tune mass damper. You have the mass of the car, you have the mass of the wheel, you have a spring, and you have a shock absorber. And if all this is working right, you hit a bump, you hear it one time, or feel it one time, and that's it, right? What happens when your shocks go out? You're no longer tuned, okay? So here's the floor. There's a second mass supported upside down with a spring and a damping element. There's some neat ones that have been used. This is what was called a pendulum tune mass damper. There's frictionless bearings back here. Springs are here on each side. There's this mass up here that can be adjusted. And over in here were air dashpot dampers. The reason for it was they put it between a raised electrical floor and the slab below. Very simple installation. And this is the result. This is walking without the tune mass damper. This is walking with it. Now the point here is, it doesn't look like this is good. But we don't have to get down to 0. We have this on-off tolerance limit at 0.5% G, roughly. So in this case, without the tune mass damper, it was way above it. In the case over here, it was less, and it was acceptable. There's a 50% reduction in energy or velocity at this location with and without the damper turned on. The damper weighed very little, so the mass didn't change much at all. There's other tune mass dampers available. These folks actually have a booth downstairs. Again, it's the same thing. There's 3 components. There's a mass in here that you can add and subtract a little bit to tune it. There are springs, and someplace there's a damping element. This is an example they provided with me. This is a long record now. This is 50 seconds, and apparently they walked back and forth across this bay a number of times. This is walking without the TMD, and this is walking with the TMD. This is a bridge in Poland. It's pretty amazing. I stayed in a hotel. I was at a conference in Poland, saw this bridge. It has 3 tune mass dampers under it. And wow, that's pretty neat. And 3 years later, I found out it was this company, and they had this neat video. And whenever you're playing videos up here, it's always tricky. That's without the TMD. It'd be nice to be able to cut it down, but I can't figure out how to do that. So you just have to watch the whole thing. I'm sorry? There's a number of pedestrian bridges in Las Vegas. They're having trouble walking up. In Las Vegas, along the strip, to prevent that kind of thing happening from 2 o'clock in the morning. They have PMDs in them. Now they can't make it. Very effective for pedestrian bridges because they're one mode, basically. And it's very, very simple response. You start putting them in an office building, it gets to be more tricky. So, oh no, how do I get out of this thing? I didn't mean to do that. Part of this AIA thing we're supposed to ask you an assessment question. And we've been told that you need to raise your hand with the answer you think is correct. And we're supposed to get a feeling for what it is and then not report it. So, we have to do this. Should the retrofit design process begin with measurements of modal properties and vibration levels? Answer A, no, calculated predictions are accurate enough. B, preferably because calculated predictions are only moderately accurate. Yes, it's essential to begin with measurements. Who says A? Come on, Doug. He's a former student. B. C. Good. All right. Yeah, you passed. With that, we have to say this again. The PhD for this session is 34717. And thank you all for attending.
Thank you. I think we have a few minutes if there's any questions, or if you don't feel like asking it now, I'm sure both doctors will stay here and maybe answer a few questions. I have a question about equipment. So a lot of this, what you're doing is walking based. So how does, when you have to test equipment like an HVAC equipment that's shaking something, how do you determine that?
Well, that's not typically, okay, the question is, all this is walking-based or human-induced vibration. What about if we have equipment-induced vibration? Well, for human comfort, that's not usually the issue. So we don't typically do that. We would say as far as the equipment goes, you just need to have the bandwidth of your analysis go up high enough. We're chopping our analysis off at about 15 hertz. We probably need to go to more at 50 or 60 hertz for that. So that's the first thing, and that's not the challenge in with the equipment, because the bigger challenge is getting the equipment to zero in low enough. So to go up a little bit is no problem, because EMEs are the ones who are making this stuff, and what do they care about? They care about higher frequencies, right? So that's not a problem. Now, the time we really find ourselves working on this stuff is say you have an MRI that's going in, and they want to make sure that the average spectrum is below some value from 1 hertz all the way to 80 hertz or 50 hertz or some number like that. And then we have to measure for the all those higher frequencies. And if one of the higher frequencies is popping up above the limit, you got to figure out which equipment's causing that and go isolate it or whatever. So that's when we are usually dealing with the equipment-induced vibration. It's not so much of a thing for walking-induced. So, or for human comfort, it's not much of a thing. It's not much of an issue for human comfort.
Is there any resource that you could help to tell voters about this issue that correlate how many people would be likely to have a problem with vibration versus how many wouldn't? Sometimes they ask, what does that mean? Is there any resource that can help answer that question?
Us.
Yeah.
Have them call us.
Haven't done any so far.
I mean, we've got an awful lot of experience with doing this, and things change from time to time, right? Now it's a problem with heavy people. I can talk to you about that later.
In one of the samples, you mentioned that you had to change the model to match, and you mentioned the models of elasticity. Like, what exactly did you change to get that? Like the depth of the beams?
Okay, that would have been in the light and lively floor. In that case, the model predicted the natural frequency to be a bit higher than measured. It wasn't a lot higher. If the model is off by a lot, then you're in trouble trying to start tuning it, because you may just be tuning garbage, right? So, but the model's already doing a pretty okay job. And so I just needed to get the frequency down a little bit. And the natural frequency is proportional to the square root of the mass over stiffness. So I just need to drop the stiffness a little bit, and that will help there. So stiffness over mass. So we just need to drop the moment of inertia some. But for me, I'm just going into SAP 2000 that we're using and putting a property modifier on the moment of inertia, and just take whatever it was there times 0.85. That's it, and run it again. So it's just as simple as that. Now we can modify the model by adding mass or doing all kinds of things. We're trying to have the minimal effect on the model, because if we have to just mutilate the model then to get it to work, then the model is probably no good anyway. So there's a lot of judgment involved in this kind of analysis, obviously.
I have a question regarding the analysis in the vibration. So for the examples you show, first is like a floor vibration. So you also assume the floor is supported all along four sides. But the other example, you're talking about the 10th floor vibration due to the bouncing at the floors below. So in that case, in your design analysis, do you still consider the facade supporting at the 10th level or facade supporting the other levels?
Did everyone hear that question?
I'll repeat the question.
There we go. I'll try. Okay. The question was, in many of our models that you saw here, we only have one floor in the model, and we have the boundary conditions that per our best judgment, or columns or pin supports or whatever. But for the multi-story building that has the vertical mode, the overall global vertical mode, you're wondering how do you model that?
Because in the other example, you're talking about the 10th floor vibration due to the people jumping on the other floors, right? So I'm just saying, in that case, can you consider the boundary condition and somehow like a facade supporting four side of provide some certain stiffness to that floor?
What do you think about that?
No.
Say no.
No, for these multi-story building problems, it has to be a global analysis. It has to be the whole building.
Right. So can we consider some certain stiffness in the glass supported floor? When I do a computer analysis, can I just usually when in the analysis you just model the columns, the beams. Can I model the glasses in the slabs?
The question is, you mean you talk about the cladding of the building? Yeah, that has to be modeled. Clearly that has to be in there. Oh, yes.
Sorry.
Clearly, the cladding has to be part of the model,
okay,
as well as any concrete walls in the building. We'll get you.
If you use active dentures, what's the drawback
Using
active dentures?
Well, tried. We're talking about such small displacements that anything I've tried to use didn't even come close to making it work. Now, maybe there's something out there today that would, but the other problem is if you're going to use that kind of damper, right, it has to be up against something that doesn't move. So, and you have to get the maximum motion. So supposing you attach this to the bottom chord of a joist and to the girder. Great idea, right? But the girder just does that. And you got it on the other side and it's actually pulling it away. So in the laboratory, we've made that kind of thing work, but we had the joist supported on just a pedestrian bridge supported on concrete block walls, put it in that location and got good results. Took it to the field and nothing.
About modeling the cladding system, I'm assuming we would just model it as dead load only and not actually model the cladding system as adding stiffness to the exterior line of the building, correct? Unless you had a real confident that it actually added some actual frilage to the exterior that could increase the stiffness of the spandrel, for instance.
That's, I've not seen a recommended modeling procedure for that. I would think that would be very conservative if you did that. I think with the displacement amplitudes we're talking about being so small, that you probably are going to get some serious help in as far as the stiffness goes. Now, as far as how to quantify that exactly, that's going to be tricky because we don't have that data.
I guess similar to how it's recommended to do partitions.
Right. You'd have something like that because you're going to have some kind of vertical like studs or mullions or something in that system, and they're going to have stiffness. And even if you have slip connections with the amplitudes we're talking about, it's not going to slip most likely. So that's going to be a big helper. Now, how exactly to model that, I don't know if anyone. So somebody somewhere probably knows that, but I don't.
What about Anthony?
Now, one of our colleagues, Anthony Barrett, he did a thesis or dissertation on finite element modeling for our types of purposes, and in his case, he had like a brick or ephes walls, and so he had vertical slip connections at the exterior studs, and these studs still behaved like partially effective load-bearing walls. We account for that in our models based on his recommendations of increasing the moment of inertia by 2.5. He just calibrated that based on the test results. And we use that for all of our models at spandrels that have any kind of decent cladding there at all. I mean, if the cladding totally bypasses the floor somehow, but it's probably not going to, then you would not, obviously. But that's probably the closest thing as far as I know of to this research, but somebody may know that in somewhere in the literature. So.
All right, thank you, everybody. Have a good night.